Okay, so we're talking about limits at infinity today. So the first example I had up there, I didn't even ask you to really solve it, right? I just put it up there to show you that as we go from positive infinity to negative infinity, right? Either way, if they said my limit was approaching negative infinity, or if I said my limit was approaching positive infinity, either way we can see we're never going to cross this line y equals 1. So way out there at positive infinity, our limit would just be 1. So if it's approaching a horizontal line, like horizontal asymptote like that, we're going to say that's the limit.
Will we have like vertical limits and like asymptotes? Kind of?
Okay, so a vertical limit would just be infinity because it'll never stop.
Okay.
Right, so if it's a vertical asymptote and the graph's going up, you know, maybe like an exponential graph, the limit's going to be infinity because it's never going to stop. It's going to go up forever. But this one, it's by the time you get out to like, you know, 1,000,000, it basically rounds to 1. It's going to be so many zeros that it's basically 1. Right? But if you go up, it's going to keep getting larger. It's never going to round to a number. That's a good question. And that's basically what I'm saying here is it's approaching a horizontal line, so we're just going to say that's the limit. Okay, and then what our video showed us last night, a whole lot easier than trying to do the limits of each individual one, would be, look at the degree of each of the variables. This has a degree of 2, this has a degree of 2, so when you're talking about infinity, the ones really don't mean anything. All right, and you're talking about millions, the ones don't mean anything. So we just look at the degrees here, they're equal, so we just take the ratio of the two coefficients. In this case, they're both 1, so my limit's going to approach 1. Right, it's like I have 1 over 1 because my leading coefficients are 1 in this case, giving me a limit of that easy. Okay, some examples on of graphs. So we can see that it's not always going to be this horizontal line, but as I go out to positive infinity, it's going to just round to this horizontal line. So we would say whatever this number is, you know, 5, 8, it's above the x-axis, it's going to round to that number eventually. Here too, as I go towards positive infinity, right, it's going to approach this horizontal line. But if I went to negative infinity, right, this line's never going to round. So if I said limit as x approaches negative infinity, well, my limit's going to be infinity. It's never going to stop. This one here, it's a sequence, but eventually it looks like it's going to round to this horizontal line, y equals L again. And we'll see some actual numerical
going the other way, don't they? But it'll get worse.
Right, so going towards negative infinity, it's actually going to diverge.
All right.
Yep. And that's just... Okay, so then this limit, as I go to positive infinity, right? So let's say 1 over, let's start at 1 over 10, right? That's going to be 0.01, or I'm sorry, that's 0.1. Right, and then 1 over 100, 0.01. Right, and then as this number gets larger and larger and larger, we're going to get closer and closer to what number? 0. So when our degree of our variable, right, this is a degree 1, when our degree of our variable on the bottom is larger than the degree of the variable on the top, there's no variable on the top, we're going to say it goes to 0 every time. So since this is the only one with a variable on the bottom, it's going to go to 0.
Wait, say that one more time. When the...
Okay, so if the degree of the denominator is larger than the degree of the numerator, we're going to say the limit as it goes to infinity is always 0. Right, when they were the same, we took the coefficients in front of both of them. Right, the ratio of the coefficients when the degrees are the same. Okay, so this one, when the degree is bigger on the bottom, it's just going to always go to 0. Yep, see, so as the numbers get larger, it's pretty much just going to round to 0. And in this graph, same thing as you go to negative infinity. It's pretty much just going to round to 0. Okay? So then here's another example. We could go through and take, remember our limit laws, we could break it up into a whole lot of different limits, but let's just say, okay, I have degree 2, I have degree 2, okay? So those pretty much cancel out, so all I'm worried about is the ratio of the leading coefficients.
What are the x, like an x and the 4x?
Okay, but still, if you squared a million, it's going to be a whole lot bigger than 4 million. Right? So that when you get out towards infinity, this smaller degree really doesn't mean anything. That's a good question too. So that's why we're only worried about the largest degree of the numerator and the denominator. Compare them. If they're the same, just a fraction of the coefficients. And I actually broke them up into 6 different ones just to show you that either way we're still going to get 3/5. It's a whole lot easier just to do the ratio of the coefficients.
Will that work every time?
Mm-hmm.
And so like, if we got asked us to evaluate, what we put our answer at, just 3/5?
3/5.
Okay.
Why does it keep skipping? Okay, they asked you to do numerical and graphical here, so basically put it in a table. You can see as I'm approaching negative infinity, what are we going to approach as a limit?
0.
0. What about as I approach positive infinity? I'm approaching infinity. It's never going to stop. Okay, here's an example of one where we cannot get, so here, oh, I thought I spelled it out for you. Here we're never going to round, right? As far as sine goes out, it's going to stay the same amplitude away from our x-axis, right? So it's never going to have a limit. It's never going to reach just one number. So a lot of our trig functions aren't going to have limits.
No limit.
No limit. Does not exist.
So if you put evaluate sine x, you just put that limit?
Does not exist. Right.
What, does not exist?
Does not exist.
Okay.
Okay, so this we had a couple people were having a question about this of a sequence. So I didn't explicitly show a video on it, but so if the limit exists, it converges, plain and simple. So if we can find a limit, then it converges. If the limit goes to infinity, right, we're going to say it diverges. So your questions will say, does the sequence converge or diverge? If it converges, find it. It'll say something like that. So for example, this sequence is eventually going to level out at our line L. Same thing here. Even though it's not at this line L initially, by the time we get to infinity, it's pretty much just going to be that line L. And we'll do some numerical examples. So again, my degrees are both 1. So what is my limit going to be of this one? 1, right? Because it'd be 1 is the leading coefficient of each of them. So we get a limit of 1. And I broke it down so you could actually see that same thing work. Does not want to go to just, okay. Then let's say we have the sequence a sub n where -1 is raised to the nth power. So is it convergent or divergent? So if I plug, this is kind of like our sine graph. If I plug a 1 in for my n, I get a -1. If I plug a 2 in for my n, I get a +1. 3 in for my n, I get a -1. Right? So if we were to graph it, it's going to look pretty much like our sine graph, right? It's never going to approach a specific number. So this one we would say diverges. This sequence. It's never going to approach a single number. Okay, how about this sequence then? This one's a little bit trickier because we'll end up having the same degree numerator and denominator, right? Because I'm multiplying my variables in the top. So if I multiply my variables in the top, what degree am I going to get? 3, right? Because I got n times n times n. And then what's my coefficient of that n to the third going to be? Can you see just by looking at it? It'd be 2. right? So the third degree, n to the 3 would have a 2. So it's kind of like, I know it's not exactly, kind of like we're getting 15 over n cubed. And n cubed is going to be times 6 times 2n cubed over 6. Right? It's kind of like we're getting that because we're not worried about all the other stuff, we're just worried about the highest degree.
Well, the instant, or.
Right, so then it's going to be the same thing, right? They have the same degree, so you're just taking the coefficients of my variables. So I'm going to end up getting 15 times 2, 30 over 6. My limit's 5.
So you can just forget about the ones within the parentheses.
Right, I mean, yeah, and I mean you'd have an n squared term, you'd have an n term, but we're not worried about those, we're just worried about the highest degree. So yeah, we'd have a whole lot more, and in fact,
Oh, wow.
right? So I broke it up into 3 different ones, you'd have a whole lot more, but eventually all we're looking for is that n cubed over n cubed, we end up with a limit of 5. Okay, I did want to do one more. So, something they may not have addressed, like let's say we had n to the 4th plus n minus 2 over n to the 3rd minus 7. If I just looked at the degree of the largest degree of my variables, right, I'm going to have the larger degree on the top, smaller degree on the bottom. So we didn't have an example of this yet. So the larger degree on the top, right, that's basically going to make this go to infinity. It'll never converge to a point. So we got 3 different ways. If the degree is larger on the top, goes to infinity. If the degrees are the same, we take the ratio of the leading coefficients. And if the degree on the bottom, the denominator, is larger, it goes to 0. It's got to fall into one of those 3 categories. Easy enough?
That was like something else we did, but I don't remember what it was. Dang. When you had to like.
Yeah, to determine the asymptotes. Yeah. See? All comes back.
Let's go.
Okay, so I'll put the questions back up. As always, if you have questions, please ask.